Hello. I'm going to show you how to solve this kind of problems. So given the two forces acting on the particle, this is the particle, small particle or object, whatever you call it, as shown in the figure, what are the magnitude and direction of the third force necessary for the particle to be in static equilibrium? So here we have to understand the question first. So this particle is under these two forces, and it appears that from the question that this particle is not at the static equilibrium, so it is moving somewhere, and to find out where it is moving and how we have to find the result of these forces. So we have to the resultant of these forces. Basically, we have to find F, big F. Let's put resultant. F resultant equals the sum of or F1, because we have only two forces, so F1 plus F2. Okay, so maybe the force will be somewhere here, and this is the resultant force Fr. That has, of course, two components in Frx and Fry. Okay, so what I'm going to do here, so after we find the resultant force, now apparently this particle has to be moving this way, in this direction. If we do the parallelogram method, we can determine this graphically, but I would like to do algebraically better. So in order for this particle to achieve the static equilibrium, we have to apply, to cancel this force basically. So how we cancel this force? We have to apply an opposite force, okay, somewhere here, the same magnitude of Fr, but what are we going to call it? F prime, let's call it F prime. So it has to be this, it has to have the same magnitude, but in the opposite direction. So when we apply this force, then we achieve, this particle will achieve the static equilibrium. Okay, that's the particle here. So first of all, let's start by finding Fr. Now we have to, in order to find Fr, so we have to find first the component of F1 and F2. So F1, okay, there are multi-steps to this, so just keep focused here. Again, we have to find the resultant of these two. So basically, we have to find the sum of F-axis on x-axis, the sum of the forces on x direction, in the x direction. And this sum is basically the F1 on x direction plus F2 in the direction of x-axis. Okay, how to find these two? Very simple. Here, let's see this. So this is the Fx. This is F1x. So this is F1x. Okay, so how to calculate this F1x? And this is the F. This is the hypotenuse of this right triangle, and this is the F1x. So look at this this angle here. So if I take the cosine of 45 degrees, this gives me equals the adjacent, which is F1x over the F1x over the hypotenuse, which is F1. Okay, and from here then F1x equals F1 times cosine 45. Okay, so here I can do the sum of Fx equals F1, so just to replace F1x equals F1 times cosine 45 degree. So what to do with F2x? So we need to find the component of F2 on x-axis. This is the one. So let me change the color here. So this is the one basically. This is f2x. And as you can see this angle here, so if I take the cosine of 65 degree, gives me the adjacent, which is f2x, over the hypotenuse, which is f2. So, but keep in mind that the f2x direction is in the opposite of the x direction. So it has to have a negative sign, right? So minus, again, f2x, which is f2x here equals f2 times cosine 65 degree. 65, I don't know why I put 64. And we put a minus here sign for the direction, and it's going to be f2 times cosine 65 degree. So what is f1? f1 is 12.0 Newton times cosine 45, which is 0.170, minus f2, which is 15.0 Newton times 0.42. And this gives me exactly 2.15 Newton. 2.15 Newton, sum of fx. The sum of fx's is the component of the frx. So frx equals, or let's put it here, fr, the resultant, x equals 2.15 Newton. Okay, now we need to do the sum of, change the color, sum of fy, okay, and the y direction. So equals basically f1y plus f2 in the y direction. Let's look at the f1y. This is f1, this is f1y. It's going to the opposite direction of y-axis. So you can take this one, or you can take this one. So there are these two triangles, you know, this is the parallelogram method. So if I take this, which this f1y, it's the same as this one, f1y. So if I take the sine of sine 45 degree equals what? The opposite, f1y over the hypotenuse, which is f1. So f1y equals f1 times sine 45 degree. So here, let me put replace f1y with its formula, f1 times sine of 45 degree plus. Now, just one thing here. This is in the opposite direction of the y-axis, so it has to have minus here. Very important, minus. Don't forget that. So then, what is f2y? f2y is this guy here. Or, if you take this triangle, it's going to be this one here. Okay, so look at this angle, 65 degree. So sine 65 degree equals the opposite, which is, this is f2y. So it's going to be f2y over what? f2, the hypotenuse. So from here, f2y equals f2 sine 65, right? So plus f2 sine 65 degree. And this gives me, so sine 45 equals cosine 45, so it is minus 1 to 12 Newton times 0.42. And this gives me, this will give me 5.11 Newton. That is FRY, which means equal sum of the component on y-axis. So we already calculated the component of in y-axis and x-axis. So let's draw this here. So this is F1 and this is let's see, kind of F2, and here FR, this is FR. And you can see here it's kind of a parallelogram here. So this is FR, the resultant of these two forces. So it has two components. One is FRX and the other one is FRY. How to calculate FR from FRY and FR axis? Look at this triangle here. So if I take the FR is the hypotenuse and FRX is the FRX is one side and FRY is another side, right? So from this right triangle here, I can say that FR square equals FRX square plus FR, Pythagorean theory, FRY square. And FR equals square root of FRY plus FRX square. And we know them, so we just need to put the numbers. So what is FRY? 5.11 square, Newton of course, square. Let's put it correctly. Newton square plus FRX 2.15 Newton, of course, square, and all square root. And this gives me, so we calculate the resultant force. So definitely this particle here is not under static equilibrium, so it is going to be moving in this direction. We don't know yet. So what is the direction? I can see it from the plot, but I need this theta. I need this direction, this angle. What is that? So we know that this the tangent of theta equals the opposite over the adjacent. What is the opposite? If RI, FRY. Okay, so it's gonna be FRY over, what is this? This is the FRX. FRX. So we know the numbers. So FRY is 5.11 Newton and FRX is 2.15 Newton. So we cancel newtons. This is tangent and theta. And this gives me 2.37, 10 theta. Okay, so tangent theta equals 2.37, and then theta equals basically the inverse of tangent, 237, and theta equals 67 degree. So here is this theta here. So if I draw it here again, this is X, this is Y. So FR, the resultant is equals 5.5 Newton, and the theta is 67 degree. Now, what I should do now to keep this point particle, to achieve the static equilibrium for this particle, what I should do? I should cancel this FR. I should cancel this FR. FR 5.55 Newton. I should cancel it. How I cancel it? I have to apply another force that has the same magnitude, but at the opposite direction. Okay, if this force is pulling this one, this force must be pulling the other side. So I'm gonna name this F prime. Okay, so F prime is 5 Newton. Simply, basically, it's equals the same magnitude of R. Now, what is direction? So direction is, you can take this angle here, find out what is this angle. Okay, and from this, from here, from the picture here, so from my drawing, basically, so these two angles here are opposite to each other. So theta and theta prime, they are opposite to each other. So they are equal. Theta equals theta prime and equals 67 degree. So F prime is about 67 degree from the x-axis in the other direction, right? Or you can say, so theta prime equals 67 degree. You can keep it this way, and it's very clear to me or anybody who can see it. The other way to report your angle is you can say, okay, you have this so you can draw your scale basically, and you say, okay, this is 180 degree. And if I have here 67 degree, then how much, because you want to say, you want to report, let's say, your angle with respect to x-axis, okay, and the third quarter, so there are 4 quarters. It will be nice to know the geometry. So this first quarter is 90 degrees, the second quarter is 180, and the third quarter. So you can report the direction of the force, this is F prime, by saying it's about this angle from the x-axis. And what is this angle? This angle is, let's call it alpha. So this angle is about 180 degree plus 67 degree. And the total gives you about 247 degree. Or 247 degree from x-axis. So you can draw, I mean, drawing will help. Let's explain something here. Let me draw the reference here. There are 3 quarters here. We know that this angle is 90 degree. So this angle here is 180 degree. And this angle here, so you're just gonna add 180 to 90, which is probably 270. Yep, 270. And here is 360. So just to understand the angles, okay, if you go from counter clockwise, okay. So hopefully this helps what we did here. So we want to know what kind of force we should apply to this particle here to achieve the static equilibrium. Knowing these 2 applied forces, we have to find the resultant of these 2 forces. So to find the resultant, we have to find the component of this resultant force on x-axis and y-axis. So we did that, and we did the y-axis. So now, since we got the components of this force in x-axis and y-axis, what we did, we used the Pythagorean theorem to calculate the hypotenuse now. Okay, because the component are the sides for this right triangle. So we got the resultant force. After we got the resultant force, this is the magnitude. So we need one other thing, because it's the force is a vector. We need direction. The direction is basically determined by the angle. So we found out the angle, and since we found the angle, this particle is definitely not at the static equilibrium, so we have to cancel that force. In order for us to cancel the force, we have to apply another force with the same magnitude but in the opposite direction. So the magnitude is just to say you give the same magnitude as the resultant force, and direction you have to find out direction based on how you want to report your force, your direction. So you can say, okay, it's about this from the opposite direction of x axis here in the negative direction, okay, in the third quarter. It has to be in the third quarter, of course. Or you can say, okay, I'm gonna report with the big angle starting from the 0 degree and going back to the third quarter.